Hello students. Welcome to the YouTube channel, Physics Simplified. In this video, we will discuss the various cases of the riverboat problems. These cases are also applicable for the river swimmer problems. So, without any further delay, let's jump into the discussion. The riverboat problem, or river swimmer problem, is a common situation that deals with relative velocity in two dimensions. As shown in the figure, the river is flowing due east. We will consider two cases here. In our first case, we consider a boatman on a boat with its engine turned off. In this case, the boatman along with the boat will be carried downstream by the river. By saying downstream, we mean that, in the direction of the flow of the river. According to the figure, the direction is due east. In our second case, we consider the engine of the boat is turned on, and the boatman is trying to cross the river. We find that, the boatman along with the boat, is now moving across the river, in a diagonal fashion. This is because of the combined motion, produced by the river current, and the engine of the boat. We will now try to analyze the motion of a boatman in a flowing river. To analyze this type of motion, we come across some specific terms. Before discussing each term in detail, we must remember, the same logical terms can be used for the case of river swimmer problems also. Now, the first term we come across is vector v suffix r. This represents the absolute velocity of the river, or the river current. We know that the absolute velocity is the velocity of a person, or an object, relative to the ground. So, we can say, this is the velocity of the river, relative to the ground, or shore. We can also consider it as the velocity of the river current, measured by an observer, standing on the shore. The second term for the riverboat problem is vector v suffix br. It denotes the velocity of the boatman, relative to the river, or water. For the case of river swimmer problem, we get vector v suffix sr. This denotes the velocity of swimmer, relative to the river, or water. Let us now try to understand what our second term actually defines. Consider a boatman on a boat in still water, or a swimmer in still water. When the boatman steers his boat, or the swimmer swims, they generate their corresponding velocities by applying their own efforts. The velocity generated due to this effort is what we get in our second term. So, vector v suffix br and vector v suffix sr denotes the velocities of the boatman and that of the swimmer in still water. Now the third and final term. For the riverboat problem we get vector v suffix b. It denotes the absolute velocity of the boatman. For the river swimmer problem, it is vector v suffix s, which denotes the absolute velocity of the swimmer. We will now try to understand the actual meaning of our third term. Again we consider a boatman steering his boat, but now in flowing water, or a swimmer applying his effort in flowing water. In this case, the net velocity of each of them will be influenced by the following two factors. Factor 1, boatman or swimmer's own effort, and factor 2, flow of water. See, this is exactly what we found when we cited the second example earlier. It must be noted that this net or resultant velocity of the boatman, or that of the swimmer, is measured by an observer standing on the shore. Now the big question, how can we find the expression of this velocity? By using the general equation of relative velocity, we can write, velocity vector of a boatman relative to the river, is equal to the vector subtraction, of the absolute velocity of the boatman, and that of the river. Rearranging this equation we get, the absolute velocity of the boatman, given by vector v suffix b, is equal to, vector v suffix br, plus, vector v suffix r. Similarly, the absolute velocity of the swimmer is given by, vector v suffix s, is equal to, vector v suffix sr, plus, vector v suffix r. So, we can state that, the absolute velocity of a boatman, or a swimmer in a flowing river, is his resultant velocity, obtained from the vector sum of the two velocities, imparted on the boatman, or the swimmer. Let us now derive some standard results of riverboat problems and their special cases. Please note that the same logical outcomes will be obtained for the cases of the river swimmer problems. Only we have to replace the notation of the boatman with the notation of the swimmer. Now, back to our current situation. We consider a river of width W, across which a boatman wants to steer his boat. Let vector v suffix br represents the velocity of the boatman relative to the river current. The boatman starts from point P on one bank of the river with velocity vector v suffix br at an angle theta from the line PQ as shown in the figure. According to the figure, the direction is west of north. Let us consider the river is flowing due east with velocity given by vector v suffix r. We know that the absolute velocity of the boatman is obtained from the vector sum of the velocity of the boatman relative to the river and absolute velocity of the river. So, the absolute velocity of the boatman is given by vector v suffix b is equal to vector v suffix br plus vector v suffix r. Considering the positive x-axis towards east and the positive y-axis towards north, we can express the absolute velocity of river as vector v suffix r is equal to v suffix r I hat. According to the figure, vector v suffix br makes an angle theta with PQ, that is, with the positive y-axis upstream. Hence, the x and y components of this velocity are given by v suffix br sin theta and v suffix br cos theta, respectively. Since the x component is directed along the negative x-axis, hence, in terms of orthogonal unit vectors, we can write vector v suffix br is equal to v suffix br sin theta negative I hat plus v suffix br cos theta j hat. Substituting these expressions in the previous equation and simplifying, we get the expression of the absolute velocity of the boatman as vector v suffix b is equal to v suffix r minus v suffix br sin theta I hat plus v suffix br cos theta j hat. Now, by using the general form of a vector in two dimensions, the absolute velocity of the boatman can be represented as vector v suffix b is equal to v suffix bx I hat plus v suffix by j hat. Comparing our previous equation with the standard form, we obtain the x component of absolute velocity of the boatman as v suffix bx is equal to v suffix r minus v suffix br sin theta and the y component as v suffix by is equal to v suffix br cos theta. Now we will calculate the magnitude of the absolute velocity of the boatman in this case. Since the x and y components of any vector are mutually perpendicular, hence, the standard form of the magnitude of the absolute velocity of the boatman is given as v suffix b is equal to under square root v suffix bx squared plus v suffix by squared. Substituting the expressions of v suffix bx and v suffix by, we obtain v suffix b is equal to under square root v suffix r minus v suffix br sin theta whole squared plus v suffix br cos theta whole squared. This represents the magnitude of the absolute velocity of the boatman in this case. Let us now calculate the time taken by the boatman to cross the river. For this, we need to consider the motion of the boatman along the y-axis. Therefore, the time of crossing the river is equal to width of the river divided by the y component of the absolute velocity of the boatman. Substituting the expression of v suffix by, we obtain the time of crossing the river as t is equal to w divided by v suffix br cos theta. Let us now find geometrically the direction of the absolute velocity of the boatman in this case. For this, the vector v suffix r is slid without changing its direction until its tail coincides with the tip of the velocity vector v suffix br. Now, according to the triangle law of vectors, the resultant velocity, vector v suffix b, is given by the third side of the velocity triangle, taken in the reverse order. Thus, the boatman will be drifted in the direction of vector v suffix b due to the flowing river, and will reach at point S on the opposite bank of the river. So, we find that there is displacement of the boatman along the x-axis, that is, downstream, when he reaches the opposite bank of the river. This displacement is called drift of the boatman and is denoted by x. Considering the motion of the boatman along x-axis, the drift is given by x equal to v suffix bx times t. Here t denotes the time of crossing the river. Substituting the expressions of v suffix bx and t, we obtain drift of the boatman as x is equal to, within first bracket, v suffix r minus v suffix br sin theta, times w divided by v suffix br cos theta. Let us now consider some special cases. In our first case, we want to find the condition when the boatman crosses the river in shortest time. In the last section, we calculated the time of crossing the river by the boatman. It is given by t is equal to w divided by v suffix br cos theta. Now, for a given river, its width w is a constant. If the boatman steers his boat at a constant velocity in the flowing river, the magnitude of v suffix br also remains constant. So, from the equation we find that the time of crossing the river depends entirely on the value of theta for a fixed value of w and v suffix br. Therefore, the time of crossing the river will only be a minimum if the value of cos theta is a maximum. Why? Because, for given values of w and v suffix br, the maximum value of cos theta gives the minimum value of the given fraction. We know that the maximum value of cos theta is +1. So, the value of the angle theta is 0 degree. Since this angle is considered with the line PQ upstream, hence 0 degree means along the line PQ. According to the figure, the line PQ is perpendicular to the flow of the river. So, to cross the river in shortest time, the boatman must steer his boat from point P, perpendicular to the flow of the river, or the river current. Now, substituting cos theta by 1, in the expression of time of crossing the river, we get the minimum value of t as, t suffix min, is equal to, w divided by, v suffix br. Now, if we want to know, in which direction the boatman is drifted, we need to find the direction of the absolute velocity of the boatman under this condition. From our previous knowledge, if we add the two velocity vectors, vector v suffix r and vector v suffix br, we get the net velocity, that is, the absolute velocity of the boatman, given by vector v suffix b. The boatman will be drifted along the direction of vector v suffix b. So, according to the figure, the boatman will be drifted along ps prime. Now, substituting theta equal to 0 degree, in the expression of drift of the boatman, we obtain the value of the drift in this case as, qs prime, is equal to, w times, v suffix r, divided by v suffix br. Let us now calculate the magnitude of the absolute velocity of the boatman under this condition. From our previous calculations, we obtained the x and y components of the absolute velocity of a boatman in a flowing river as v suffix bx is equal to v suffix r minus v suffix br sin theta and v suffix by is equal to v suffix br cos theta. Now, under the condition of crossing the river in shortest time, the x and y components of the absolute velocity of the boatman becomes v suffix bx is equal to v suffix r and v suffix by is equal to v suffix br. Now, from the velocity vector triangle, the magnitude of the absolute velocity of the boatman is given by v suffix b is equal to under square root v suffix bx squared plus v suffix by squared. Substituting the expressions of v suffix bx and v suffix by, we obtain the final expression of the absolute velocity of the boatman. It is given by v suffix b is equal to v suffix r squared plus v suffix br squared. In our second case, we will find the condition of zero drift of the boatman. Let us try to understand the meaning of the term zero drift. It means that the boatman wants to reach at a point on the other bank of the river, which is just opposite from where he started. To find this condition, let us first write the expression of drift of the boatman in the flowing river, which we have calculated earlier. It is given by x is equal to, within first bracket, v suffix r minus v suffix br sin theta times w divided by v suffix br cos theta. Since the drift is 0, hence x must be equal to 0. Now substituting the expression of x, we find that the fraction w divided by v suffix br cos theta can never be 0. So, for the equation to be valid, v suffix r minus v suffix br sin theta must be equal to 0. Simplifying, we get sin theta is equal to v suffix r divided by v suffix br. Therefore, theta is equal to sine inverse of v suffix r divided by v suffix br. So, if the boatman wants to reach at point Q on the other bank of the river, which is just opposite of point P from where he started, he must steer his boat at an angle theta given by sine inverse of v suffix r divided by v suffix br from the line PQ upstream. Let us try to find out what will happen if the boatman steers his boat at an angle theta to the line PQ upstream. When the boatman steers his boat at this given angle theta to the line PQ against the river current with relative velocity vector v suffix br, then due to the influence of the river current, the absolute velocity of the boatman vector v suffix b becomes directed along the line PQ as shown in the figure. The corresponding velocity vector triangle will look like this. From this velocity vector triangle, we find the magnitude of the absolute velocity of the boatman as v suffix b is equal to under square root v suffix br squared minus v suffix r squared. Let us now calculate the time taken by the boatman under the condition of zero drift to cross the river. Since the absolute velocity of the boatman is now directed along the line PQ, therefore, the time is equal to width of the river divided by magnitude of the absolute velocity of the boatman. Substituting the necessary expression, we find the final expression of the time as t is equal to w divided by under square root v suffix br squared minus v suffix r squared. Now, we will try to find the necessary condition for the zero drift to happen. We know that the value of sin theta can never be greater than 1. So, for the boatman to reach directly at the opposite point on the other bank of the river, the necessary condition is the magnitude of the absolute velocity of the river can never be equal or greater than the magnitude of the velocity of the boatman relative to the river. In other words, we can say that if v suffix r is greater than or equal to v suffix br, the boatman can never reach point Q. Let me explain why. If the magnitude of the absolute velocity of the river, that is, v suffix r, becomes greater than the magnitude of the velocity of the boatman relative to the river, that is, v suffix br, the value of sin theta becomes greater than plus 1. This is not possible because no such angle exists. Again, if v suffix r becomes equal to v suffix br, the value of sin theta becomes equal to 1. So, the angle theta becomes equal to 90 degrees. Practically, it is not possible to cross the river and reach point Q by the boatman corresponding to theta equal to 90 degrees. Why? Because, from the figure we find that, in this case, the boatman will move only upstream. Moreover, we find that, if we put v suffix r equal to v suffix br, and theta equal to 90 degrees, in the expression of the magnitude of the absolute velocity of the boatman, it becomes 0. So, from the above discussion it is clear that, to cross the river, and directly reach the opposite bank point, the magnitude of the absolute velocity of the river must be less than the magnitude of the velocity of the boatman relative to the river.